Hey there, calculators. Mr. Leavenworth here, here to talk to you all about graphing functions, which is something you've been doing for a long time, probably all the way back to middle school. But we are going to use some calculus to help us kind of flesh out exactly what a graph should look like. Sometimes we're given a lot of information, like the function's rule or its equation, and sometimes we're given just its derivatives, which is a different type of problem, and that's actually the type of problem we're going to see first. Before we get there, I wanted you to be aware of kind of these 9 different things that we should always be considering when we look at a function. So we're talking anywhere from domain, symmetry, is the function even or odd? We're definitely going to look at derivatives. We're going to look at critical points or maybe even inflection points, increasing, decreasing, concave up, concave down, all of those things. And then back to the traditional kind of algebra 2 and pre-calc stuff. Local minima, local maxima, horizontal, vertical, maybe even oblique asymptotes. And then, of course, the intercepts often come into play. Sometimes they do and sometimes they don't. And we're going to see 2 different problems, 2 very, very different problems that kind of explore graphing functions in 2 different ways. These 9 different pieces here that are on the screen right now, you don't have to memorize these, but these are definitely good guidelines for moving forward as you're graphing functions. So we are going to move down to the first problem, which is not your traditional function graphing. It is saying, hey, we have all of this information about the first and second derivatives of a function. We are told in the directions here that the function is continuous. And then we're going to, it says even very specifically, use a number line and then sketch a possible graph. All right, well, so let's do that. Let's use a number line first. And so here we go. And the numbers that we're going to put on this number line depend on the information given. The problem says we're continuous from negative infinity to positive infinity. So we can denote that here. It's kind of obvious sometimes, but it doesn't hurt to write it down. And then we're given 6 different intervals or 6 different points. And here we go. So from negative infinity to 0, from 0 to 1, from 1 to 2, from 2 to 3, from 3 to 4, and from 4 to infinity. So we have these numbers here, and I'm actually going to spread these out a little bit just so we have some room to work. And that'll give us some space. What we're going to do here is we're going to use the information of the derivative. So for instance, our first interval here says our first derivative is negative or less than 0. So I know instantly that my function is going to be decreasing. But its second derivative is positive. So I know that on that interval, our function is concave up. And I'm actually going to go ahead and do this for each interval that I see. Let's see, first derivative is positive, and second derivative is positive. Concave up as well. On my next interval, first derivative is positive, and second derivative is negative. And then we'll just keep going. We have a negative first derivative and a negative second derivative. Second to last interval here, we have a negative first derivative, so we're decreasing, but we have a positive second derivative. And then finally, on our last interval from 4 to infinity, we are increasing and concave up. Now, this seems like it might be weird information to deal with, but even though we don't have intercepts or anything more than this derivative information, we can still get the good shape of a graph. And the only thing that ends up mattering are these x values, 0, 1, 2, 3, 4, and we'll extend this out a little bit. And here we go. Here is a trick that my AP Calculus teacher taught me way back when. If I have a decreasing and concave up section of a graph, I was actually taught to like physically erase or cross out the part that isn't decreasing. And so if I want the increasing part of concave up, I'm going to get rid of that. And you can kind of see what become like these different pieces of our sketched graph. And so I am just erasing the part of the concavity that doesn't make sense here given the information for my first derivative. And so what I have, I'll use, let's use a green. And so from negative infinity to 0, I am decreasing in concave up. So I'm going to kind of look like this. And I know my graph is continuous, so I'm going to have to pick up from there. From 0 to 1, I am increasing. And I'm going to get all the way to 1 with this. And from 1 to 2, I'm increasing, but my concavity flips. So I'm going to kind of have a shift there. And then from 2 to 3, I am decreasing it in concave down. Again, we don't really know much about the steepness or anything like that, or the intercepts, because we don't have that information. But what you're seeing here is quite a bit of detail, at least in terms of the shape of the graph and how it looks. Definitely a quartic graph here. And then from 4 to infinity, I am increasing and concave up. And you'll see that the pencil strokes here are not clear. It's really like a sketch if you do any sort of drawing or painting. But what we can do is really rough out the shape of this graph and get something like what I have here. All right. We're actually going to break this into 2 separate videos. So this is going to be part A, just this problem for problem number 1. You can go to video B for the second problem, which is a lot more detailed kind of investigation of what graphing a function looks like. Thanks for being here. Talk to you soon.